Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to work the question, count islands. This prompt states that you want to write a function that takes a matrix as the input, and this matrix is going to have two types of characters that represent land and characters that represent water. Then you want to find the total number of islands or connected land pieces and return that count as the solution. Let's understand our data. So land is going to be represented by the hashtag or pound sign. Then water is represented by the tilde. Land is considered connected and part of the same island when they touch horizontally and vertically. So here's one island, and here's two islands. However, land that touches diagonally are not considered part of the same island. So in this example, we have one island here, then 2, 3, 4. So the best way to get the intuition to solve this question is think first how you would do it by hand. So if you had this matrix, you would probably start to scan, find a land piece, then find all the connected pieces of land to that and count that as an island. Then you would continue to scan and do this for each group of land in the matrix. So starting here, you would look, then you would find this land piece. Then you would start to look left, right, up, and down and see which ones are connected to it. After accounting for the land pieces, you would then increment your island count and then make a note of the ones that were connected so you don't double count them. You would continue on, find your next island group, account for all the land, and then make a note that those have been used. Then finally, you would find this last island piece, get to the end of the matrix, and realize you found 3 islands. And this thought process and logic is exactly how our algorithm is going to work. We'll start to iterate through the matrix. Then when we find a land piece, we'll iterate from there, look left, right, up, and down for every piece in the graph, and then account for all the ones that are connected. We also will need to mark when we've seen them, and then continue on with our iteration. So iterating through a matrix is something we know how to do. We just walk it one item at a time from beginning to end. But then when we encounter this land, how do we iterate from there? How do we find these other connected pieces? We can't just continue to go from left to right, because that's not how these islands are constructed, and we wouldn't really be able to tell which ones are connected that way. So let's highlight all the pieces. And what data structure does this look like? It actually very much resembles a graph. Each node in this graph can have 4 neighbors. It can be one to the left, up, right, and down. It's also non-linear because we don't know the number of items in the graph and they can be connected in different ways. So we'll now use graph traversal to find all the nodes that are connected. So that is the first step to our logic. We iterate through the matrix. When we encounter a piece of land, we then traverse through all the connected pieces as if they were a graph. Should we use depth first search or breadth first search? Either would work. In this case, we'll go depth first search. It's usually assumed to be better in memory, and it will allow us to solve this either iteratively or recursively. After we account for a piece of land within an island, we need to mark it as used. This will prevent us from double counting it and getting the wrong answer. So what's our options? Well, we have a type of piece in the graph that we always just ignore and skip over, and that's the water piece. So if we flip these land pieces to water pieces, then as we continue to iterate, they'll no longer have meaning. They'll just be ignored by our algorithm. So every time you encounter a new node in your graph, you just flip it to water. So now let's walk through this matrix and apply our algorithm logic to it. We start with the first node, and we scan the matrix. Then we encounter a piece of land. Anytime we encounter a piece of land, we increment our island count. Then we traverse this island as if it were a graph. Every node can be connected possibly left, up, right, and down. As we hit each node, we flip it to a water piece. When we iterate this graph, it's going to be done recursively. So what are our base cases going to be? When do we stop iterating? Well, we stop when we hit a water piece, so that implies the edge of this island, or we also stop when we hit the edge of the graph. So our 2 base cases are reaching the edge of a matrix or reaching a water piece. Those are all now flipped to water, so we continue our scan. Let's skip ahead. And now we encounter another land piece. This means we found a new island. We increment our count, and we scan it. They're all flipped to water, and we continue our iteration. We find another piece of land, we increment our count, and then we're done. So we return 3 as our solution from this function. So we treat this question like a matrix question and a graph question. We iterate through the matrix, but then when we find a land piece, we iterate through this island as if it were graph nodes. We increment our count, and then we traverse the graph and flip every land piece to water. This prevents us from double counting. Once we reach the end of the matrix, we should have the total island count, and we can return that as our solution. Our time and space complexity is m times n, where m is the number of rows and n is the number of columns. We get the time complexity because we need to iterate through all items. When we perform our graph traversal, we'll touch each item again, but this would be at most twice per item. So it would be approximately 2m times n, but we drop constants. For our space complexity, we're using recursion, and in a worst case, we would add all m times n items to the call stack. And now we're ready to implement our solution function, countIslands. The argument to this function we call map, and this is just the matrix of our land and water pieces. We'll start by declaring 2 constants, land and water, and this will just make our code more readable and explicit. First, we check if we have a valid map, if we have rows and columns. So if there's not a map, or no rows, or no columns. If this is the case, then we just have no islands, so we return 0. Now we want to iterate through all the items in our matrix. We go through all the coordinates for our rows and columns. So the number of rows is just the length of our matrix. The number of columns will be the number of columns for any row. And finally, we need our island count. We initialize this to 0. We begin iterating through our matrix. We go through the rows. We go through each column item in a row. If it's a water piece, we do nothing, so we only care when we find a land piece. So if we found a land piece, we increment our island count. And now we need to depth first search, traverse all the land pieces within this island. So we'll call that now and then implement it. So mark land as viewed, depth first search. We need the map to iterate through it, and we need to know the row and column we're at. So now our function, and the first thing we'll account for is the base case. So when we hit the edge of the matrix or we find a water spot. To find the edge of the matrix, it's going to be 0 or the number of rows or columns. So we do what we did before. Num rows and num calls. We know we're outside the matrix when we're less than 0 or when we're greater than or equal to the number of rows or columns respectively. So our base case, if is outside map, or we found a water piece. So our current location is water. If this is the case, we simply return and end the recursive search in this direction. Since we didn't return, that must mean we're on a land piece and we must flip it to water. So set the current item to water. So now we want to depth first search in each direction, left, right, up, and down. So we'll just grab our function, pass our map, and then when we go left, it's row -1. When we go right, it's row +1. Going down is call -1. And going up is call +1. And then we return once we're done with that recursion. So this is our logic. We iterate through each item. When we find a land piece, we increment our count, and then we traverse all the land pieces of that graph using depth-first search. First, we check our base case. Are we still inside this graph? If we are, we know we're on a land piece. And now we flip it to water, so next time we hit this piece, we simply pass it by. Then we continue to traverse left, right, up, and down, and once all directions have hit the terminating condition, it returns and our loop continues. Let's run our code. We need to return our island count for it to work. And we're done. We successfully iterated through this matrix and counted all the islands. Thanks everyone, and I'll see you in the next lesson.